Today I'm going to talk about some extreme geology and some of the effects that it creates and why these are interesting things to study. I want to point out before I begin that there's a whole bunch of people on board that have been on this adventure, both within Curtin and elsewhere. So for those of you that don't think or don't study planetary science generally, you might start with a question of why is it an interesting topic to study? For one, all solid bodies in the solar system have evidence of impact processes. The very planets came together by accretion a long time ago, and so impacts are a fundamental geological process that it's still ongoing. The extreme pressures and temperatures create all kinds of interesting effects in the crust. They can turn the crust inside out, flip it upside down, bring deep-seated rocks to the surface many tens of kilometers in a matter of minutes to seconds, and so create some interesting landforms. Of course, with big impacts, there's environmental consequences, some of which affect life. We're all familiar with the dinosaur killing impact in Mexico. We'll see some products of that impact later on in the talk, and so that's of consequence. And of course, in WA in particular, we're interested in economic resources, so I'll draw a line between impacts and economic potential of craters in a little bit. What I want to do tonight, providing time, is to first go over some general ways to view or think about Earth's cratering record. So we'll talk about a little bit about the distribution. Of course, we're going to spend some time looking at Aussie craters because that's where most of our time is spent in my group. We'll touch on some economic potential that has been demonstrated previously. And then I want to spend a fair bit of time talking about the namesake of the title of the talk, Accessory Minerals, and how they're changing how we think and what they're able to allow us to access in regards to a variety of different processes related to impacts. So this is an image from one of the more common databases that's publicly available, the Earth Impact Database, and it just is a snapshot of what the terrestrial cratering record looks like now. These aren't big numbers. There are about 200 craters that have been confirmed to date. That number isn't very special, and the cool thing is it is creeping up with time. And so new crater discoveries are on the order of 1 or 2 per year, and so this number continues to change, which is good news for us, job security perhaps. You can see that the distribution of craters is not uniform across Earth. There's a pretty direct correlation between, let's see here, between where the people that study craters live and where craters have been found, right? So there's a lot of parts of Earth that clearly there's probably old rocks and lots of craters around that simply haven't been discovered. And of course, most of the ocean basins, no craters have been found. Yes, the rocks are younger, but there are a few marine impacts that are known. You can easily take the data from Earth Impact Database to play with and do things with. This is just a quick plot that shows the relationship between the land mass of these regions listed on this database versus the number of confirmed craters that have been reported. And you can see that of these regions, we're sitting on one of the smaller land masses considered, and yet we've got a pretty fair number of impact craters. I'd say we're punching above our weight class here, certainly in comparison to some of these other areas. Again, you can probably attribute that to just the amount of attention that these regions have received historically. But I look at that as potential, plain and simple. Here's some of the things that you face if you want to do this for a living. For one, like a lot of different aspects of geology, the record's fragmentary. There's lots of reasons, burial and tectonics and erosion, that work against preservation of craters. We've only been able to find 200 thus far out of many, many more that must have existed on Earth. So that's an issue going forward. Fortunately, the community of people that does this, and this is going back many decades, long before I got on board, have developed a pretty rigid criteria for getting a suspected site over the line, if you will, and into that category of a community recognized confirmed impact origin. Basically, it comes down to finding some kind of geochemical signature that represents a contribution from the meteorite, something dissolved in a melt typically, that cannot be created in the crust by any other means, or some high-strain shock deformation that forms during the process. And I'll spend a fair bit of time talking about that subject today. The other issue is that very few craters have been dated properly or within good precision or accuracy. My colleague at Curtin, Fred Jourdan, who's an argon geochronologist, has published a handful of papers emphasizing this topic, trying to bring it to the attention of the community that of the known craters, less than a quarter have accurate and precise ages that have been determined. And this is challenging. It's not for lack of trying, my goodness. Typically, it's for lack of appropriate material to date. If we switch across to the record in our backyard, this is a figure from a brand new review paper that's out now by Riza, who just introduced me, that shows the paper is a new review on the Australian record. And it catches up to date everything that we found to date, at least that's been published. And so here it is on the backdrop of geology, all the cratering sites. I'll point out that there's just over 30 that have been confirmed. This is agreed upon in the community. And of those, about half of them are in WA. I put a plus sign there as a cheeky little note that we're going to make that number bigger really fast. We have a lot of things in the pipeline, and that number is going to change between the next year or so by more than a digit. Here's some of the sites that are active, working on, many of them in WA and a few across the border. And so these are some of the areas that we've put quite a bit of attention on in recent times. It takes a village to do this. My goodness, this is just a few of the crazy crater hunters at Curtin and some of our associates. I want to call out a few people here that really are integral to the process. Jason Myers has been integral in our work at Ora Banda and some other sites that I'll talk about. You know this character, she's sitting here next to me. Wallace Mayo, I also saw him out in the audience. He's an honors student at Curtin working on Yarrabubba, which we'll get onto in a bit. This is Morgan Cox, another PhD student who's working on the Woodley crater and about every other place she can possibly find material from. Colleagues Chris Kirkland and Nick Timms and I in the shrimp lab at Curtin, where we date materials that I'll talk about in a little bit. Former student at Curtin, Timmons Erickson, now at NASA JPL. A fair number of images I'll show today are works that he did while at Curtin or in his job at NASA. I don't think these two characters need an introduction in this room. I saw one of them out here earlier. Peter and Mike Wingate have been involved in a number of things that we're doing, which is really great. In terms of resources, my talk's not about this subject, but I have to mention a few things for those that aren't aware. Craters around the world provide potential to explore for oil and gas and even water resources, but the big ticket items are metals, particularly gold and nickel. Most people probably have a sense that a lot of gold has been mined in the Witwatersrand Basin in South Africa. Okay? When I say a lot, I mean something on the order of 40,000 tons, which corresponds to about a quarter of all mined gold. What a lot of people may not realize is the entire Wits Basin is contained in one gigantic meteorite impact strike named Friedefort that occurred there 2 billion years ago. And it created the scenario where the Wits Basin was preserved, because the Wits Basin would have originally extended beyond that location where it is. These extensions have eroded over time and are gone, but what's preserved inside the impact basin is everywhere being mined. It's a slightly different story at the Sudbury Nickel District. A lot of people recognize that Sudbury is one of the nickel mining centers of the world. Last year, I think Canada and Australia were maybe 5 and 6 on nickel producers globally. I think Australia was 5, Canada was 6. And of the production in Canada, about half of that production comes from an impact structure. Sudbury Impact Complex, this gray unit here, is a melt created during that impact 1.85 billion years ago that scavenged the nickel. Without the impact, not a drop of nickel to be mined at Sudbury. The interesting thing is the age of the bedrock in both cratons I just talked about is about the same as much of the bedrock age across the Yilgarn, about 2.7 billion years. And so it really begs the question of, is there anything else like this undercover? And that's something that can't be ignored as an exploration topic. All right. I want to switch gears now and focus a little bit on accessory minerals and how we go about our business on some of these topics. These are typically not minerals that you talk about when you want to study shock deformation. More often you hear of people studying shock quartz and other features. But accessory minerals have fundamentally changed how we approach the game. Many of these are datable materials. They're uranium-lead geochronometers, not all of them, but many of them. And one of the things about it is that if you look at a phase diagram for either bedelite, well, zirconia, or zircon, you can see that here's the conditions in the crust. And in impact events, we can create materials in conditions that extend so far beyond crustal metamorphic conditions, we can probe all kinds of processes by looking at these phases. And I want to get more onto that here. Of the accessory minerals, the title of the talk is cheeky, some type of revolution. What that means is we're bringing online a whole series of impact recorders and chronometers that simply have not been in the conversation previously. Here's some of them that are pretty new. These are the noobs, if you will: titanite, xenotime, apatite, all known accessory minerals. They're familiar to many of you, perhaps. All known uranium-lead geochronometers with variable levels of application. But just recently, we've realized that they also record shock deformation. A lot of accessory mineral studies are done with backscattered electron images on an SEM. I'm not going to show many of those images tonight because the main tool we use to document the high strain, damage, and other changes is electron backscatter diffraction. It's where an SEM beam scans across a polished sample and generates diffraction patterns at every pixel very rapidly. With that information, you can do two fundamental things. You can identify what the phase is that you're analyzing. It's a diffraction pattern after all. And you can also tell something about any changes in the orientation of the crystal. So armed with those two fundamental pieces of data, you can tear into things. This is a grain of titanite where the color indicates changes in orientation. This happens to be from the Mexican impact at Chicxulub. And all of these linear lamellar features are deformation twins formed by the impact. And so the titanite is responding to that high strain environment. It does not form some of these twins from any other process, and so they're a diagnostic feature. Here's some work Morgan Cox has done on xenotime, another uranium-lead geochronometer, from quartzite up at Spider. This is far up in the Kimberley. Bugger of a place to get to, but it's really a great place to go visit if you have the time to get there. The deformation twins here in xenotime are a new phenomena not found outside impact events. They've been reported by our group from a couple of different sites, and we can see how the orientation data are displayed on pole figures. I'm going to try not to say the C word tonight, crystallography. This is apatite over here, and again, the color changes in the apatite image show bending of the crystal lattice along these PDBs, planar deformation boundaries, and its strain caused by impact that we can quantify the effect and we can quantify the crystallography of the strain. In other minerals, we can do even wilder things. Impacts create these high temperatures and pressures and often momentarily stabilize polymorphs, minerals with the same composition but either a tighter or a looser crystal structure, depending on whether it's a high P or a high T of phenomena. But once everything calms down, the polymorphs often revert back to something stable at ambient conditions, and so they leave no trace, or at least unless you analyze by EBSD. In each of these cases, this is, on the left is a zircon that was dropped into a very hot impact melt from a site in Canada, an impact structure. And the edge, so the core of this is a zircon. Those are some Sims pits here. But the margin of the zircon dissociated. It got so hot it split into its constituent oxides, zirconia and silica. And what it is today is bdelliite. But the bdelliite has a systematic twin behavior to it. It's not random. You can use software to recreate how it achieved those twins. Those twins are formed because the bdelliite was something else, and it reverted back to the twinned bdelliite. As it turns out, the something else can be worked out to be cubic zirconia. That's never been found in nature, by the way, even though some of you might have it as jewelry. One of the reasons it's not typically found is because it requires temperatures above 2,000 degrees to stabilize. It's an extremely hot mineral. Okay? It's no longer present, but its footprint is. Timmons Erichsen found a monazite from the Ries crater in Germany that had lamellar twins. But and again, the twins themselves are a deformation phenomenon. But he noticed with EBSD that the twins themselves were twinned twins, a classic evidence of reversion from a different phase. And again, the same software that we use that can process orientation relationships reconstructed that to a tetragonal form of monazite. That's a new mineral that has not been found. We haven't found it in this case, but we found the footprint of it. Okay, so that's pretty exciting, a brand new monazite phase, polymorph. I've done a few studies on Libyan glass, and I'll talk more about that in just a bit. But we've applied the same thing, the same type of analysis to systematic twinning in alpha cristobalite, the low temperature phase that forms during cooling, to be able to learn more about how the high temperature phase, beta cristobalite, forms. You almost never find beta cristobalite preserved because it transforms back to alpha cristobalite during cooling at about 270 degrees. So you don't find it, but we find its footprint here. And so we can study minerals that no longer exist, document their existence, and feed those into what we do. There's probably no better poster child for this than zircon. Many of you are probably familiar with zircon. It's used widely for dating and lots of different purposes, provenance studies. It happens to form a fantastic polymorph named Reidite that is stabilized at above 20 gigapascals in crystalline rocks. Okay? So during shock compression, zircon partially converts to Reidite, and since we've been throwing electron backscatter diffraction at the problem, we've been able to find Reidite in a number of places. It's a rare mineral. There's probably maybe 10 localities on Earth, and all the Reidite that's ever been discovered could probably fit under your fingernail. So it's not an abundant mineral. Someone asked me, are you going to go mine it? I said, oh boy. But one of the things about finding it is we can characterize how it relates to zircon, how zircon transforms. And it does it through a very simple relationship of turning 90 degrees about this direction in zircon. On a pole figure, you can see the data for zircon are co-located with the data for Reidite, but they're rotated 90 degrees. Okay, big deal. Why is that important? Well, here's how it looks on a schematic. If this hurts your eyes to look at, I'll set an alarm. I'll wake you up in about 30 seconds. The interesting thing is we've been able to take these relationships and we've packaged it into a concept called phase heritage. Basically, it's finding evidence for phases that no longer exist. In this case, it relates to zircon transforming to Reidite under shock compression and Reidite reverting back to zircon, because Reidite is not thermally stable above around 1200 degrees. 1200 degrees sounds pretty hot for the crust, but that's a low temperature in an impact environment. So if you have a zircon with Reidite in a rock that ultimately melts, you can easily achieve temperatures twice that or higher. So what happens to a zircon with Reidite in that process? Well, here's the zircon on the left, a single grain, vertical c-axis. Up to 2 orientations of Reidite, that's the blue guy here, can form in a single zircon, each orthogonal to the zircon c-axis here by this relationship. But if that zircon gets a little hot around the collar, if the Reidite gets hot around the collar, it's going to come back to zircon, and it has to do it by the same pathway. So each Reidite can come back to zircon via one of these 90-degree relationships. So 2 of them are shared, which happens to be the same as the original one. And the end result is you create a very strange-looking mineral that has 3 different orthogonal orientations present in it. What does that look like? This sounds very esoteric. Have you ever found such a thing? We find them everywhere we look now when we examine impact melts. It took a long time to figure out what in the heck was going on with these grains. These are different granular zircons that now consist of these little neoblastic domains. They're about a micron across, more or less. And they're an absolute riot of color when you analyze their orientation. When you do that and you look and see what's under the hood, if you look just at the c-axis, you can see for this guy 1, 2, 3 orientations of zircon in a single grain, 90-degree relations. For this guy, this is Ackerman in South Australia, 1, 2 orientations, 1, 2, 3 for the guy from the Brazil melt, and 1, 2, 3 from Louisiana Congo. A similar pattern again and again. Sometimes the data are more dispersed, other times they're tightly clustered. But we see this as evidence of former Reidite. It went to Reidite and it came back. All these are from impact melts. In order to say that with a lot less words, we decided to package it into a cheeky little model called FRIGN zircon, which stands for former Reidite in Granular Neoblastic Zircon. It's an orientation-based identification. We start with a zircon under some level of shock compression. It can form up to 2 orientations of Reidite. Here's their c-axes relative to zircon, 90-degree relationships for you crystallographers. When things get hot, when that grain is in a rock that melts, everything goes neoblastic. All the Reidite orientations have to go back to zircon either this way or that way, and the one down here goes over there or over there. And so you create 3 orthogonal relations. Okay? It's the only way you can make this. If it remains hot, you can even dissociate the grain a little bit, and we've seen that in a number of places. As it turns out, FRIGN zircon's pretty bloody good for dating an impact. People rapidly recognize that the extent of recrystallization expels the pre-existing radiogenic lead. And so once you do your orientation analysis, you can go in and do spot analyses, and remarkably precise impact ages, even for relatively young craters, have been determined. And so there's a little bit of a renaissance now of dating impacts by first finding zircons, if you can, that display these features. The concept of using a neoblastic recrystallized grain to date impacts has been applied previously. Here's the case for monazite. We don't have a cute little name yet for monazite. And the different colors here show parts of the grain that recrystallized, and in this case yielded an impact age for this particular site in Brazil, Araguaia. Not all accessory minerals need to recrystallize in order to yield useful geochronology. Here's a study of a shock twin titanite. This was a project led by Nick Timms, colleague at Curtin, and from one of these Chicxulub granitoids. And you can see the pretty twins in this grain here. There's twins across this. And we thought we'd, put 1 or 2 spot analyses on the grain by laser ablation. Never do half measures, right? And the interesting thing is when we plot the data on a geochronology plot, if you're not used to looking at age data on this form, this is a type of a Concordia diagram with uranium and lead isotopes. Apologies. But you can see that these data are wildly dispersed. There's data all over the shop. One of the things that this cone-shaped data does is it forms a cone back to a common lead composition derived from the feldspar in the same rock. The lower boundary of that cone regresses down to about 300 million years, which is the age of the basement in this case. But it's the upper boundary of the curve that's experienced the most, what we interpret as impact-generated lead loss. When you regress a line through common lead and the upper analyses, you get an age of 67 plus minus 4, which overlaps very nicely with the 65.5 million year old age known for this impact. The fact that it didn't recrystallize led us to conclude that in this case, what happened here is all the fracturing and twinning allowed for hydrothermal alteration and lead leaching by those means. Not all the data define this line. A lot of it is only partially reset. So there's a lot of opportunities here. All right. I want to take the last little bit of time and just cover a few topics that are recent and kind of fun. The first one is back to Libyan glass. It's not very often, in my experience, that you get to take your favorite strange esoteric interest and find a real-world application. If you can do that, you're just on a good roll. In this case, it's a story of how shock zircon is providing insight both on some archaeological interest, but more relevantly on hazards from space in the form of near-Earth objects and the threat that they may pose. For those that aren't familiar with Libyan glass, it's actually found in western Egypt in the Libyan Desert. And it's this bright yellow canary glass. It's a high silica natural glass that has no analog anywhere else. It's nearly pure silica, usually greater than 98 or 99%. Makes sense that it's a pretty quartz-rich source that formed it. It was first reported just under 100 years ago in the scientific literature, and the origin of it's been in question for a long time. Howard Carter, when he was busy raiding King Tut's tomb, removed a lot of objects from the burial chamber, including this amazing pectoral piece, this little chest piece. And note that central scarab. He described it as a bit of yellow quartz. Not far from the truth, but not quite right. In 1996, an Italian team received permission from the Egyptian government to haul in a bunch of Raman spectrometers and other non-destructive analytical gear to analyze the composition of this, and it turns out, guess what, it's Libyan glass. So 5,000 years ago, the royals of the land thought this was pretty cool stuff to study, so we weren't the first. The interesting thing about Libyan glass is people argue fiercely about how it was made because it's so unusual. The models kind of range from melting of a target during the formation of an impact crater, but that doesn't really fit well because, for one, there's no crater that's been found anywhere close to the field, nor has anyone found evidence of shock deformation within the glass. Nor do any other craters in quartz-rich target rocks have they found similar glass to this. And so it's a mystery. It's given rise in the last 10 or 15 years to another model, and that is one of an atmospheric airburst. Perhaps some of you remember the event over Chelyabinsk, Russia, about 8 years ago, where an NEO ripped across the sky, caused a lot of property damage, human injury, and that airburst deposited about half of a megaton of energy into the atmosphere. The models for Libyan glass are that it was a 100 megaton airburst event, an event humans have no concept on how to perceive, something that would be catastrophic if it occurred anywhere near people. So governments have been depending on the frequency of these events and counting Libyan glass as one such event in their hazard assessment. Well, what do? We got on and do what we do best. We got some of this material, mounted it, found that it does contain zircons. They're hard to find and they're awfully small, but they're present. They are granular, backscatter image. When we analyze their orientations, they're full of pretty colors, and guess what? They're bloody friggin' zircons. 3 orthogonal orientations. So it's a clear signature that Reidite was present in the source material. It's a high-pressure mineral. High-pressure minerals require a shock wave. A shock wave requires a crater. This rules out formation of this by an airburst event because they don't generate shock waves on the ground. They do melt the surface, but no shock waves. And so we concluded when we published these data that the governmental agencies worried about NEOs, which is a pretty reasonable thing to worry about, honestly, probably should not consider Libyan glass in this threat assessment because it's a different process and impacts occur on different intervals than airbursts do, thankfully. Closer to home, some of you may have heard about a new impact in the goldfields by Ora Banda. I don't think I really need to explain the location of Kalgoorlie to this crowd. In fact, a lot of people may have been out there the last few days for diggers and dealers. Ora Banda is about an hour north of town, and we're just out there in April doing some field work. This is in conjunction with Jason Myers. He's one of the earlier people that recognized that some of the materials found there may have an impact origin, so we've been working closely with Jason. Riza's working on this project as well as part of her PhD, and so it's with great pleasure I can share a wee bit of data. I can't steal her fire. It's not very nice for an advisor. Here's what's known so far. Some of the early data is that there is a geophysical anomaly there. There's about a 5-kilometer gravity low with a little high in the center of it. And so the size of the feature is about that. Here's some of the mines that are there, nickel mine and gold. It's in these greenstones in the Kalgoorlie super terrain. And some of the target rocks here are the bent tree basalt and the Mount Pleasant sill. And so these are rocks that are well known, and they're all about 2.7 plus or minus some change in age. And the site's been drilled. Some of the most encouraging things that you want to find when you rock up to a new site are shatter cones. These are among the only macroscopic evidence you see of shock deformation in rocks. Here's some in outcrop. You can tell they're oxidized, and some in core. This is the bent tree basalt. Lithic breccias that are polymictic, meaning different rock types, that also contain glass. So these dark bits are glassy nuggets. You can see they're cracked. Some of it's massively hydrated. And Riza has succeeded in finding what we think is shock quartz by SEM. We're in the process of properly documenting that. And so all of the ingredients you want to find to confirm this. This is an impact structure. There's no other explanation. Right now, the only data that exist are an abstract from earlier this year at the Lunar and Planetary Science Conference. I'm sure she would be happy to provide you a copy of that if you ask her. The last thing I want to touch on is probably what I would modestly say is one of the more interesting impact cratering finds or discoveries or recognitions in Australia in some time, and that relates to the Yarrabubba structure, which is just up the road from us a few hours. It's now recognized that this is the oldest asteroid strike on the planet. Let's just stop and massage that one more time. Digest it, taste it, try another little nibble. The geological heritage of Australia continues to amaze. This is Barlangi Rock, which is very readily accessible from early in April. Wallace, in the back of the room, is doing an honors project on some mapping of these rocks, and so we were just up there recently. It was with great pleasure that John, where are you at? John Bunting, here he is, came over and shook my hand earlier, and he said, "Oh, you're going to talk about Yarrabubba?" And it's like, yeah, wow, you're one of the earliest guys on the scene. 20 years ago, Francis McDonald and John and others were kind enough to publish a really solid paper on this site that said, listen, here's an aeromag anomaly centered around Barlangi Rock. This is the sandstone road. Meeka's up here, sandstone's down there. We found some funny looking things in the quartz, some shock quartz. There's shatter cones in the outcrop. That thing they call Barlangi rock, we think it's actually impact melt. This is an impact crater. Wow, cool. They suggested it was large, and they proposed an age of early Proterozoic. John and I were just talking about that. They did some zircon work, and they found mostly inherited basement ages of 2.5, 2.6, 2.6.5, 2.7, ages not unusual for the Yilgarn, and a single grain at about 2.23. And he said, well, it's hard to say what the age is. Early Proterozoic. Well, they got the right answer 20 years ago, but not enough data to back it up. Last year, Timmons Erickson and a group of other people went back and revisited Yarrabubba rocks and did another geochronology campaign and nailed down that age bang on at 22-29 million years, 2.23, and we got a big story out of that. Here's some of the nuts and bolts of how that worked. Back to our accessory minerals. On the left are some zircons, on the right are some monazites. The top row is one of the shocked granitoids at Yarrabubba. The bottom row is a sample of that Barlangi rock. It's a granophyre, it's got quench textures, it's the impact melt rock as we now recognize. And in the granitoid, you can see the zircons look reasonably respectable. They have some twins, evidence of high strain shock deformation, and they yield old ages. Monazites as well, these red lines on the orientation maps are twins. The monazites do have a little incipient neoblast form. They're starting to recrystallize. Even in the granitoid that did not melt, we see younger ages in these domains and older ages where it's just highly strained. So these grains are complicated. John, this stuff is a dog's breakfast if you don't have a map of what's going on in it. In the impact melt rocks, it's a little more straightforward. Almost all the grains are neoblastic. They've all recrystallized generally. And here's zircons that all yield that 2.2 age, and the monazites are highly neoblastic. A few strain zones still left, and they yield that similar age. Here's what it looks like when the data are plotted out. This doesn't happen to me very often, where you analyze two different minerals from the same rock and you get the same age. My God, you must have done something wrong. The neoblastic monazite yield a very tight age, 22-29 plus 5. And the zircons yield a slightly less precise age, but one that overlapped. And this is the age that that melt rock formed, ergo, this is when the impact event occurred. I think this might be my last slide. Before that study, Vredefort in South Africa, where the gold originates, was the oldest impact structure known on Earth, 20 million years. Yarrabubba is over 200 million years older. That's a big step, actually, not forward, backwards. That's a big step back in time. But what's more interesting is the context of this age. If you look at what's going on globally, it's an interesting time period. It's kind of in the middle of when the Earth was starting to breathe for the first time with oxygen, and so there's no causal association with that that's obvious. But there's an interesting magmatic lull at that time. A global lull in magmatism for about 50 million years was recognized and published in Nature about 3 years ago, unrelated to this study. And as it turns out, Yarrabubba's bang on in that window of a magmatic time period. Nothing going on. However, if you look over here in blue, these are Paleoproterozoic glacial time periods. There's several of them that are known. They're variably preserved glacial diamictites at different parts of the planet. But that age of Yarrabubba overlaps the end of the youngest Paleoproterozoic glaciation. People had argued and published lots of papers long before us about why did Earth come out of these ice ages? How did that happen? Because the next ice age is not even on this time scale. It's 400 or 500 million years into the future, into younger times, rather. And so here's a large impact event at a time period when the Earth had a lot of ice on it. And so we posed a question, a hypothesis. Could the Yarrabubba impact event have had a climactic change? And the answer is it might work. We ran some numerical models that featured an impact into several kilometers of ice. We don't have evidence there was ice at the Yarrabubba site, but if the glaciations were global, low latitude glaciations, it's a reasonable assumption to find ice at that location. And for an impact structure of around 70 Ks, you end up injecting a lot of water vapor. 10 to the 14, 10 to the 15 kilograms of water vapor into the atmosphere. Is that enough to change climate? This is where it gets tricky, and you need to be a climate modeler, which I'm not going to pretend to be that. It depends on how high up in the atmosphere it goes. If it stays low, it can precipitate out as rain and snow. If it goes high and resides there, you can insulate the Earth and heat it up and melt ice. And so depending on the scenario, depends on what kind of climactic effect. But the stage is set for a potential trigger to have a climactic effect where none had been proposed previously. So like all good science, we don't have all the answers, but we've laid out a hypothesis that's incredibly intriguing. Thank God it passed peer review and is available for further testing. Of course, just because it passes peer review doesn't mean it's right. All right, I think that's the end of the business. What I want to do is thank you folks for coming and say goodnight to your new friends, because you should all go home now and decide to change careers, especially you young folks, and study your new friends because of how fun and interesting you now realize that they can be once they get smashed by a rock from space. And the last thing I'm going to say, let's see if it comes up, is I would be doing a disservice not to advertise an incredibly significant event that's happening. The countdown has started. 14 days and counting. Tomorrow will be 13 days. The Space Science and Technology Center at Curtin has a program called BINNER, which builds spacecrafts, and in 14 days, Western Australia's first spacecraft will be launched. Let's say that one more time, please. Graduate PhD students in the SSTC, that's our center at Curtin, have built cube-shaped satellites, CubeSats they're called, from scratch, built by students, not bought with crap off the shelf. They've built the detectors, they've built the batteries, they've built the solar panels, they've built all the systems involved from scratch. And one of these has been shipped to the Japanese Space Agency, where it was then transported on a module to Cape Canaveral. Right now, it's sitting on top of a SpaceX rocket, waiting to launch in 14 days. It's going to launch into space on a SpaceX rocket to the ISS, International Space Station. When it arrives there, astronauts are going to pull off this CubeSat built on campus by HDR students, open the shuttle bay, deploy it into its mission, where it will go through and test some technologies that are on it. And it has cameras, of course, because we're crazy about cameras. Take a selfie and take pictures of Australia while testing the technological capability. I'm not kidding. Literally watch that space. 14 days. Thank you.